Thank you. Thanks for the introduction, Misaki, and thanks to the organizers for the invitation to come to a great conference. Yeah, so this work I'm going to be reporting on is joint with Andrew and Harshit. By the way, Harshit is now on the job market. Andrew, of course, is no longer on the job market, but Harshit is, and he's very strong. So I would strongly recommend Harshit. Yeah, job possibility. Right. So I'm going to talk about exotic tensor categories, exotic factors, that kind of a thing. So it's not because exotic. I'll try to explain what I mean by exotic in a few seconds. It's not that exotic is such a that an exotic um, subfactor is better in some sense than a non-exotic one. It's just that it's different. So what I think is a sickness of this whole world is a lack of examples. So our fusion categories, our subfactors, there's not enough weird examples. Our VOAs, conformal nets, there's not enough weird examples. And so this, imagine trying to develop like 100 and some years ago, trying to develop group theory, finite group theory. If all you knew were abelian groups, then you'd be led to wrong conjectures. It would be so when you start to discover that there are weird kinds of groups and that you have ways to construct weird kinds of groups that maybe have some interesting properties, then the theory really starts to take off. And so that's what I'm kind of thinking maybe this area needs is more examples. So that's the spirit here. So an exotic by an exotic, well, here, this is an example that I think many of us would agree is an exotic fusion category. It comes from the whole group subfactor. So you get two fusion categories. One is way too complicated, but the other one is very simple. And so it has this other fusion category has three simples, all of them one alpha and alpha squared. These are group-like, so alpha tensor alpha is alpha squared, etc. And you have some non-invertible, some call it rho, and then you have alpha rho and alpha squared rho, and this is it. So this has rank 6. It's a semi-simple category, a fusion category. It obeys sort of dihedral-like symmetries. I guess I should call this 2, this one. So it's not going to be braided, obviously. The last one I have to mention is what about rho tensor rho? And rho tensor rho is going to be 1 plus rho plus alpha rho plus alpha squared rho. So these are the fusion rules for the whole group fusion category. So this is what I would call exotic. Exotic isn't a definition. It's just it's a feeling. It's like love, right? You know, when you're there, you know that 5 years later, you're pretty sure that wasn't love. So exotic. So it's an exotic subfactor. So what I would mean by an exotic fusion category is just something that doesn't have a construction using usual stuff like finite groups or Lie theory. So quantum groups at roots of unity give you very nice fusion categories, much nicer than the whole group, really. But there's generic constructions for these things. So the idea of an exotic fusion category is just something that you have to work hard using really terrible methods to construct these things, with the idea that when enough bright people, see some of these other examples, they can see what's really going on and come up with generic constructions, which will then move the posts. So what was exotic will suddenly become non-exotic, generic, boring, and et cetera, et cetera. So the idea is just to search for enough fusion categories, for example, that look like the whole group, and then hopefully see patterns, notice things, and then go from there. So in this spirit, Masaki, there's at least 3 constructions of the whole group fusion category, and so Jingwei, I'm sure disagrees with me, but for me the most interesting is the one that Masaki proposed somewhere around 2000 or something like that. And so this is using the Kuntz algebra. So for the whole group, you'd use the Kuntz with 3 plus 1 generators. 3 is the order of the group Z mod 3. So there is a group here, but it's barely a group. It's Z mod 3. So you can't use group theory to construct the whole group. So it's exotic. Okay, so Saki's idea was you let G be an abelian group, finite abelian group. And you generalize this in an obvious way. So now you have invertibles that are parametrized by your group. They form, their fusions are given by the group G. So you have alpha G, alpha H. Tensored with alpha H is equal to alpha GH. You have a non-invertible. In fact, you have n non-invertibles. The fusion rules are the obvious ones. So alpha tensor rho is rho tensor alpha inverse. So if you use additive notation, it would be minus G. And then we have this one, which looks like so this is what so any fusion category that realizes these fusions, any categorification of this fusion ring, we'll call whole group Zoomy fusion category. And so Misaki wrote down a way to classify all of these things. So the data that you need in order to do this isn't important for my talk. I'm just trying to fill time because I didn't have time to prepare my. So you have a bunch of matrices. These matrices are G by, I should write it like this. These matrices are parametrized by elements in your group. And you have a number of these matrices. The number of these matrices is G quotient 2G, sort of the 2 rank part of your abelian group G here. So you have a bunch of these matrices. I'll just write it like this. Again, the details aren't important. And you also have some signs. So the signs, again, parametrized by G and H. And then you have a bunch of roots of unity. These roots of unity are again parametrized by this. And there's lots and lots of identities that are satisfied. And so these identities are things like, well, here's one of them. So A, G, H, K is equal to A, G, K, H. And there's quadratic identities in the A's, the A bars, and there's cubic identities in the A's and A bars, and some identities involving these things, and that's it. So you get a blob of lots of variables and lots of equations that have to be satisfied. And if you can manage to find a solution to these equations, then you have a fusion category of whole group Izumi type. And there's a equivalence, there's a very simple equivalence relation on which solutions are going to yield tensor equivalent fusion categories. And all of them, conversely, all of these are going to correspond to solutions to these equations. So you can describe this family of what I would call exotic fusion categories reduced to solving a bunch of equations.
These are unitary.
These are unitary. Yeah.
There could be other stuff non-unitary.
That's true, actually. So yeah, yeah, you're exactly right. So so this is a complete classification of all unitary categorifications of these fusion rules. So I think it's great. And so there's been some work on classifying these things. I'll just mention some very quick things just to give you some feel for it. If you take G to be, you can see that odd groups behave nicer than even groups. So I'm going to restrict myself to odd groups. So if you look at the integers mod 3, then it turns out there's 2 unitary categories. One is the whole group subfactor, so subfactor associated to the whole group, and the other one is Morita equivalent to it. I don't know, just call it another. And this was found, I think, first by Grossman and Noth. And so that's what happens for Z mod 3, and the story for Z mod 5 is similar. And so some of these correspond to subfactors and some of them don't. And Wasaki also explained which ones correspond to subfactors. So we'll call our fusion category of subfactor type. That just means the fusion category is going to be, if you're given a subfactor, you have two different Morita equivalent fusion categories. And so so subfactor type is an if and only if condition on whether the given solution here is going to correspond to a subfactor, one of the fusion categories associated with a subfactor. And what it corresponds to is it fixes. So it fixes the zeroth row or the zeroth column. It's more like it's the same thing of your matrices. So if it's of subfactor type, so one of these will be of subfactor type, the other one is not of subfactor type. So this is all understood.
Sorry, Terry, I don't quite understand. These are unitary things.
Yeah.
Why they're not subfactor typed?
So what I mean by subfactor type is it's the even sectors of a subfactor. And so this one is so there's three fusion categories in the Morita equivalence class of the whole group. And one of them is, so two of them are the subfactor ones. And then the third one has the same fusions as this, but it's not it isn't part of a subfactor. Yeah. What I mean by subfactor type.
So you might, and even sectors of an irreducible subfactor.
Yeah.
Unitary fusion
Yeah.
even sectors, which is maybe what you were.
That's right. So and there's lots and lots more solutions. I'll talk more about it later. So I would say that the whole group is an exotic subfactor, and this is a time-dependent statement, and I like nothing more than for someone, hopefully me, to conclude that the whole group is not an exotic subfactor after all. That's one of the goals of this kind of work. But it's not an exceptional subfactor. So it belongs to an infinite tower. There surely are missing constructions of fusion categories of subfactors. And if you apply this construction to Z mod 3 or something, you turn the crank, you get the whole group subfactor. So the whole group subfactor is exotic, but not exceptional. And in another 5 years, hopefully it won't be exotic either. Okay. So now I'm going to do some simplifications here where we've probed this a little bit more. And so this is old. This is what's kind of old stuff. So it's from, I don't know, 2017 or something like that. So I'm going to be talking, most of my talk will be about some new construction, so things that are post this. But let me just say some things about what's been done in this direction, just to put it into perspective. And so let's focus on. So let's restrict to odd G. So our Healing groups are going to be odd, just because it simplifies things a bit. Let's restrict to subfactor type. I'm using subfactor type because I want to generalize this to non-unitary way. And so then you have no chance to be actually part of a subfactor, but you still have sort of the combinatorics of a subfactor. So that's why I'm using this slightly obscure terminology. So let's restrict to odd G and of subfactor type. And then in this case, like we have a pretty good classification of these things. So we've constructed a number of so G then is going to be some cyclic group. Actually, we're going to also restrict to G cyclic. So G is going to look like Z mod n, where n is some odd integer. So this is simplifying everything just to get a feel for what's in this family. And so we have potentially a complete classification. So for small n's, it's a complete classification, and for other n's, it looks pretty safe. It looks like it's probably a complete list. So we've done this for n up to 29. And so, for example, and we can also drop So I've already told you the answer. So if you looked at Z, if you look at n equals 3, then you'll find that there is exactly one thing that survives, one thing in this class, because the Grossman-Snyder fusion category isn't of subfactor type. So there's only one thing that survives, it's unitary, but you can look at its Galois associate. So any fusion category will be defined over some number field. And so you can hit the quantities. That means you can, everything, associators, whatever, can be defined with your matrices. Once you've chosen a basis, you can choose your basis that these matrix elements lie in some field, some number field, and you can hit that number field, choose any Galois homomorphism of that number field, and you get a new fusion category. Maybe it's tensor equivalent, maybe it isn't. And so you can do this, and you get a second fusion category. This will be non-unitary. So the dimension of rho you can calculate for yourself. The dimension of rho is going to be n plus square root of n squared plus 4 over 2. And this Galois automorphism flips the sign of this. So it's definitely non-unitary. The non-invertible has a negative dimension. And so this is what happens.
This is a third one.
Sorry?
This
This
is
is
third
n
one.
equals 3. This is,
There you said there are two unitary, and this is a third one, which is not unitary, but is of subfactor type.
that's right. So here you have a non-unit. You similarly have, you can do the same thing with Grossman-Snyder. So really the complete classification, this is a theorem, complete classification in Z mod 3 is two. You have two unitaries, one of subfactor type, one not of subfactor type, and two non-unitaries, one of subfactor type, one of not. And the non-unitaries are connected to the unitaries by Galois.
Ah,
And it's a similar story for Z mod 5. And in fact, there's all kinds of patterns here. This is the reason I'm burdening you with all this. There's a lot more structure here than it looks like. That's why there's something going on. And so, so when it's the case that n is prime, the two numbers that are important here are n and n squared plus 4. So if both of these are prime, this happens more often than you'd think. So for example, when n equals 1, 3, 5, 9, 13, 17, all these satisfy this condition. So when this is the case, then you get a nice answer. So there's, what you find is that there's 2 times n minus 1 fusion categories. But there's this equivalence relation. And so you end up with 2 inequivalent ones, tensor inequivalent ones, exactly like 3, 1 plus 1. This is unitary, where the dimension of the invertible is plus sign, and this is non-unitary. The dimension is minus. This is what happens in this case. And you could say more. There's a whole bunch of structure that's going on. So the field, so I said that these things, any fusion category is defined over a number field. So this is an important part of the story, actually. So the field that that these are defined over is an abelian extension. It's not cyclotomic, but it wants to be cyclotomic. Nothing wants to be cyclotomic more than the fields of the Ogre-Bazumi fusion categories. So it's an abelian extension of Q adjoined this number here. It doesn't matter which sign you take, obviously. So it's almost a cyclotomic field. Okay, there's more I can say, but I'm wasting too much time on this old stuff. Yeah, so I'm just giving this as an example, but you can say if n is prime and this is the product of two distinct primes, then blah. And if n is prime, but this is the square of a prime, then blah. Like there's all these things and it all looks nice, and very clean and tidy, and indicating that there's clear structure. So an indication of what kind of structure is going on here comes from the centers of these categories. So part of the charm of the this Kuntz formulation of these fusion categories is the tube algebra works out very beautifully, and you end up with easy ways to capture the modular data of the centers of these categories. So the centers of these fusion categories, we can work out the S and T matrices, and what these end up looking like is something along these lines. I'm just going to give you the heuristic answer. You get a bunch of ones, so T is of course a diagonal matrix. You get a bunch of ones, you get a bunch of nth roots of unities, and you get a bunch of n squared plus 4th roots of unity. You can be much more explicit. And S matrix looks like this boring stuff. Essentially, things like cosines with ends in the denominator. And you have things like cosines with, as you'd guess, things like n squared plus 4 in the denominator. So there's an abelian hidden here, is in the double, is an abelian group of size n squared plus 4. And of course, we're handed a group of order, an abelian group of order n. That's what we're starting with, and there's a bilinear form on these abelian groups, and that's how you build up the S matrix and the T matrix. And you can go backwards. So as I say, it's much more explicit than this. You can look at what are the possible S and T matrices. Forget trying to solve these difficult equations. What are the possible modular data that looks like it's supposed to look like? And you write down your answer, and you'll find that if n is prime and n squared plus 4 is prime, then there will be exactly 2 different possibilities. And they'll correspond to the doubles, the centers of the modular data of the centers in these solution cases. So that isn't a theorem, but it's been verified up to 29, as I say. So this has lots of repercussions, lots of suggestions. It says that the construction of these categories, the fusion categories, is going to be very difficult. The actual the entries A, for example, of the matrix A. Here, there's only one matrix A because G is odd order, but these entries look completely random. They solve polynomials which look completely random. There's no pattern that I can see, anyways. So the fusion categories look pretty hideously complicated, but their centers those centers are going to be nice. So that's where our construction will happen. We'll be able to construct the centers of these Hogru-Pazumi fusion categories and then pick the square roots to get the fusion categories. That's the way our construction will work. Okay. So I think that's all I want to say about these. I mean, there's a lot more I could say about this, but. So the problem with all this is that it's hard to solve these equations. You can go pretty far, but still, to go off to infinity, I think there's no person that would, there's no one surely that thinks that these things stop at 31 or something like that. So this goes on to infinity. This is an infinite series, and much more is true. It's a nice infinite series, an easy to understand infinite series that we're just too dumb, frankly, to understand right now. Okay, so that's that. And so what makes this hard is that it's hard to solve these equations, these cubic and quadratic and whatever equations. It'd be trivial to solve them over the integers, right? In fact, you'd get no solution would be the answer. No solution, no solution, no. But it would be easy to solve them over the integers. What's kind of curious is there's a theorem called Frobenius, some other old person's name, density theorem. And this says that this implies in this context here that if there's at least one solution to Misaki's equations, so there's at least one solution in the complex numbers, of course, that goes without saying, to those equations.
Sorry, Ty, but this equation with the conjugate, you have also in non-unitary case, or?
Yeah, that's right. So we'll talk about that very shortly.
Okay.
In fact, we'll talk about it in about 1 minute or so. Yeah, exactly. So that's the problem. But if there's at least one solution to these equations, over, let's just temporarily ignore the bar, and I'll give the proper answer to this question in about a minute. If there's at least one solution to these equations, then for positive density of primes, there's an integer solution, mod p. There's a solution in Z mod p for this. This is an incredible theorem. In fact, there's a lot more going on here than just that. For example, the density of primes is 1 over the size of the degree of this extension. So you know the density, or if you can figure out what the density seems to be, then you know the order of the Galois group, that kind of a thing. So there's a positive density of primes where you get an integer solution to these equations. You don't know, unfortunately, which primes are going to work, at least until you know more about the solution. But so that suggests that we should be looking at solutions mod p. Right? And so there's a theorem. So this is the first new method. There's a theorem. This is due to Eddinghoff in I think 2017. And this theorem says that let funny f be split, whatever that means, non-degenerate, whatever that means, fusion category. We all know what that means. Over some field K, we have in mind fields of positive characteristic, things like Z mod P, finite field or something. So let F be a split, blah, blah, blah. I'll explain what these words mean in a second, but I want to get to the punchline. If R is a local ring with R quotient, this is fancier. This is the theorem. So it's as fancy as it needs to be. We'll dumb it down shortly. So if you quotient your ring by its unique maximal ideal, then you get the field here. Sorry. You get the field here. Then you can lift if you're not so confident about these words, that's not important. Then you can lift this fusion category over what to us will be finite characteristic, in fact, a finite fusion category. The fusion category over R, or really the field of fractions. So I have to define a few words here. Non-degenerate is very simple. Non-degenerate just means the global dimension. So the global dimension squared. So the sum of the squares of all of the dimensions of the simples is not equal to 0. So no matter what your field is, you can talk about dimension. These are just the eigenvalues of your, so they won't lie in your field in general, they'll lie. And a fusion category just means the usual, just copy down the usual definition. So we want all the Hom spaces to be vector spaces over this field. So K to some power, et cetera. Everything is semi-simple. Split just means that that Schur's lemma applies. So for example, something that's not split would be the representation category of the finite group Z mod 4 over the rationals. This isn't split because here's a simple in this category. It's the two-dimensional rep that sends. So this, if you were to try to diagonalize this, you'd have to bring in i's, which don't lie in the rationals. And so this is simple. But of course, when you extend this field, then this decomposes into some. So Schur's lemma. So this is not split. So that's my definition of split, just this example.
That when you extend the field,
Extend the field, then simple stays simple. That's right. That's. And so if your thing satisfies, if your fusion category satisfies split and the global dimension isn't zero, then you find some local ring. So well, what I mean by local ring, let's suppose that your field. Let's do some examples. I'll find how to do this with some examples again. Let's suppose your field is Z mod P, or I should say FP. This is your field. Then I could take called it R. I could take my field of fractions is going to turn out to be, I called this, I didn't give it a name. The field of fractions is going to be the rational numbers. The local field is going to be, I'm going to take the integers and I'm going to localize it with respect to the prime P. So the local field R is going to be all rational numbers with denominators coprime. You know that a lot of you of this stuff that you saw maybe as an undergrad, or maybe you've never seen it. Again, the details aren't important. Just trust me, these aren't obstructions. So you can do this more generally. In fact, if R, so more generally, I don't have time to get into this unless someone is passionate, wants to know about it. But if so for any finite, finite field that you take, then I can find a number field, so a field of finite degree over the rationals, such that if I look at a prime, I take some prime, I look at some prime ideal over that prime, that means, and I look at the ring of integers for this number field, and I localize with respect to that prime ideal, then I get an R that works, that satisfies all these conditions. Conversely, if I start with any number field, then I can choose any prime such that some FQ is the result of this, the reverse of this construction. Maybe it'll be clearer when I get to the application of this idea. So it's not important if you don't completely grasp it. I'll do the deciphering for us. So what we want to try to do is look at solutions to Masaki's equations over a finite field. Now, as Sebastiano pointed out, we can't. I mean, it's a dishonest thing to try to do because these equations involve complex conjugates. And so, but the solution was worked out by Dai and me a few years ago. We looked at, the reason I focused on this class of odd G subfactor type is because of this theorem. So this theorem is what allows us to apply Eddinghoff's theorem. You can parameterize. You can do the Izumi equations. Well, we found the Izumi equations for whatever I wrote down up there. So for G odd, our solution is complete if it's cyclic. If it's not complete, if it's not cyclic, then you have to ramp it up a little bit, which we didn't work out. So let's just stick to cyclic for now, and subfactor type. But Masaki's equations dealt with the unitary case. And so these are not necessarily unitary. And of course, these are categorifications of the full group Izumi fusion ring for that odd cyclic group G. You get a bunch of equations and they look very much like Masaki's, except of course you don't have complex conjugates anymore. And now you can apply Eddinghoff. And so what you get is this result. So So choose your favorite prime. You have to be careful. P can't divide the order of your group. And P can't divide, and P can't divide n squared plus 4. Otherwise, it's going to divide the global dimension, which is a bad thing. It won't be non-degenerate. Then any solution to the mod P equations. So the non-unitary, I'll just call them the non-unitary equations. So the equations that Di and I wrote down. Any solutions to these things give not necessarily unitary, categorical. Sorry, give fusion category over some finite field. Q is some power of P. You can't restrict yourself. You can't assume that your answer is going to be integers in FP. In general, it's going to be some extension of FP. Of course, we know by Frobenius that if we're lucky and we chose a good prime, then it'll be integer valued, but in general, it won't be. Okay, so you get a fusion category, and that means it'll be split, it'll be non-degenerate. We'll be able to apply Eddinghoff, and this will lift to a fusion category over field of fractions of blah, blah, blah. So some number field, in fact, over C. There's a uniqueness that you get here. And conversely, if you have some fusion category for the complex numbers, then for any P that doesn't divide n and doesn't divide n squared, maybe I should just write n times n squared, 4. Is a solution in some finite field of characteristic P to non-unitary equations. So the classification can be done over a finite field. It can be done in characteristic. Oh shit, I'm running out of time. Hey, so I have to speed this up. There's other things I wanted to say that I think were more interesting. Okay, so there's more for me to say. The tube algebra picture works out, and so you can get the S&T matrices from in mod P as well. So for these odd groups G, P equals 2 is a natural choice, and then you get some weird things happening. You get so because these are odd groups, you only have a single matrix. Multiplying by 2 because it's an odd group is invertible automorphism of this group. So this thing is going to turn out to equal AGH to the 4th power. This is a Frobenius automorphism. This is a field automorphism of our finite field FQ. So there's as always, there's all kinds of structure here that I don't have time to get into. And so this is much faster than over complex numbers, as you'd hope. So, for example, Grosvenor basis for n equals 11. I can't do that over the complex numbers. It takes 5 minutes to do it over characteristic 2. And again, so these ones will always involve extensions. Finite fields won't involve F2. They'll involve FQ, where Q is some power of 2. But of course, there's a positive density of primes where you actually get integer solutions. I can't find a pattern for that, so I kind of dismiss that. So I think for now, I think the interesting direction is to look at the most positive direction for me is to look at characteristic 2. Okay, I'm running out of time. I forgot that I don't have an hour. I have only 45. Sure, you guys are all very glad that it's just 45 minutes. So I'll very quickly summarize the second method. I had 3 methods I wanted to discuss, and so I won't be able to discuss the third. Well, maybe I'll give one sentence to it. So so this is method 2. So as necessary as it is for us to find examples, exotic examples of fusion categories, even more desperate is to find exotic examples of finite tensor categories, so the non-semi-simple fusion categories. So this isn't interesting to subfactor people, but it's interesting in math phys, it's interesting to VOA people, etc. So this is a method, non-semi-simple. I'll call them fusion categories, but the fancy word for them is finite tensor category. And the point is that the Kuntz method works. Actually, it's not Kuntz, it's Levitt. It's the same idea. And so the idea is you build up, you look at the data. So it's very similar to what you did in the simple case. You look at the data for simples and the projective covers. So the non-semi-simple fusion categories, so the fusion categories, everything is contained in the simples. If you understand the simples, you understand everything. For the non-semi-simple fusion categories, there's a lot more going on than just the simples and the projective covers. There'll be finitely many simples that will have their projective cover, but will be continua of non-decomposable, indecomposable non-simples. So you'll have all kinds of other modules. But if you forget all that, that's just technicalities, and you just study, you analyze in this sort of a way, the simples and their projective covers. So for every simple, you have an endomorphism on some algebra, a Levitt algebra, and for each projective cover, you'll have an endomorphism. You just study the properties of these endomorphisms the way that Misaki and others have done for these for the fusion categories. Then you write down equations very similar, not that much worse than what you get for fusion categories. And that only gives you a piece of the finite tensor category. But now you use a result of a very recent result. This 2021. So in a talk in Edinburgh, there should be at least one paper written by a Scotsman. And so that's my token Scotsman here. And so you can then apply what they call abelian envelopes. You can apply it to this subcategory that you get, the category of the simples and their projective covers. So it's a nice finite category in every sense of the word. And then you get a true finite tensor category. So a non-semi-simple fusion category. Whose simples and projectives and their fusion rules are the ones that you modeled up here. So it's a way to extend this subcategory, this very accessible subcategory, to the full finite tensor category. So I haven't worked out any examples. I started playing around with the case of 2 simples, the tensor unit and something else that squares to 1. And they both will have a projective cover that's non-trivial, and you start playing around with it and you flesh out the equations pretty quick. And then you try to find solutions to these equations, and the whole story goes through. You can take the centers of these things and get your modular tensor category. So that's the second method. And I'll just say in one sentence, the third method is it's natural to go from properties of simple structures and apply them to give us information about complicated structures. So for example, knowing about tensor categories tells us about conformal nets or VOAs, but it's great when you can use the existence, say, of some complicated structure like a VOA, say, to tell you something about about non about the simpler structure like a shadow. And so you can do that in this world, I think. So you can look at there's VOAs that have you can define over the integers. This, in fact, rational VOA is surely definable always over the rationals, and only finitely many primes do you need to invert. So you can take mod p residues of any rational conformal any rational VOA, and then look at the category of representations of this thing over bad primes, over primes you're not supposed to take. You likely will get a non-fusion category, a non-semi-simple fusion category, which is defined over characteristic P, and then you use the Eddinghoff trick to lift it to a finite tensor category over the complex numbers. That was my third method, but sorry, I went over time. So I'll stop there.
Thank you very much.
Terry, have you tried to maybe like actually construct weird VOAs over finite fields?
I mean, that'd be pretty cool to be able to do that because it's hard to construct VOAs over C. And so you'd think that over a finite field, say Z mod P. So I've only looked at it in the opposite direction where you have something like a lattice VOA where that's defined over it's defined over the integers. The moonshine module is defined over the integers. And then you can take the reduction mod and any prime and you get a nice VOA. But it might not be rational anymore. And so that's what I've looked at. But it'd be kind of cool to try to do it the other direction.
Even in the direction you do it in, do you still get like character vectors and you like reduce the coefficients mod P, or does that whole modular structure break down?
Yeah, so I haven't pursued it that far yet, but you should get so you still get vector spaces, and so you still get graded dimensions, and Jou's proof of modularity of these things was an algebraic analyticity. So it's very possible that the whole story runs through. You get something that what modularity would mean isn't you have these transformations, fractional linear transformations, but rather that they're solutions to some differential equation. So yeah, I mean there should be a shadow of all that story for rational VOAs over nice primes, and then if you're doing it over bad primes, then like primes where the representation theory kind of breaks down. Easing over P equals 7, the famous example, where the representation theory breaks down. It shouldn't. The VOA looks totally wholesome, but for technical reasons it breaks down. And so there you probably don't get a rational VOA. You probably don't get a modular fusion category over second center. Anyways, yeah, it'd be fun to explore that more.
Any other? I have a maybe I don't quite understand what you're saying about method 2. You're saying that you have these symbols and projected cover, but also talk about double, right? And
Yeah.
you claim that double is also a modular tensor category. So
Yeah, so there's a Decoupe paper from 2024 which discusses taking the center of
the modular tensor category have finite number of simple objects.
yeah, I believe that there's conditions that have to be satisfied, but yeah, I think that yeah. So I mean he covers that. He explains that when is the center of your finite tensor category.
That's interesting. You start with something which potentially have continuous family of representations.
It does have a continuous family of representations. That'll be guaranteed.
And then in the end, you take some kind of double, you get the finite.
Yeah, that's right. So I haven't looked at his paper. All I know is the punchline of it, which says that you get a sensible modular fusion category, or sorry, modular tensor category. Actually, it's a modular tensor category, so probably it also has continua. So it's not a modular fusion category. It's a modular tensor category. So it's
So what does modular mean? That
modular means that the S matrix is non-degenerate.
But S matrix would be infinite dimensional.
No, so you define it over for the simple. So there's better ways to define what non-degenerate would mean. But so for example, for a C2 cofinite VOA, the that'll give you, that representation category will be a modular tensor category in this sense, a non-semi-simple modular. So it'll have continua of representations of VOA. A C2 cofinite VOA does have continua of representations.
Oh, you mean the SL2Z representation?
Yeah, the SL2Z representation will be finite dimensional.
So this is because you take the entries of the matrices are just a simple object. The component.
Well, yeah, it's more complicated. It's a little more complicated than that. You have to augment it with, some people call them pseudo traces. So Miyamoto was one of the people that fleshed out this. So you have to expand it a bit. Yumashenko did it first. So yeah, you have to get a little bit more than just the simples, but you can get a finite dimensional representation of SL2Z. T won't be a diagonal matrix anymore.
Any other? So if there is no, let's thank Terry again. Next talk will start at 10:30. So here you. The fix where P.
Did you see the mail? Yeah. Luckily, I think we had to. Well,
Sorry?
maybe if they say something, we it's
Oh,
I think we will.
I haven't pushed, I haven't had time to.
Yeah. So I think we should.
So I have no, I have no,
Do
so.
the one that you told me.
Yeah, I mean, it,
One in York.
so I mean, it seems better, it seems faster than complex, I mean, it is faster than complex numbers. I'm not so interested in pushing it to 35 or something, that's kind of.
No, I mean, think what is better for you. I mean, if it's better, Rome. I mean, don't think in the.
Intention of the field is the same. I mean.